As we are studying the ability of energy to be transformed from one form to another form, really what we're doing is, next slide, we're looking at thermodynamics, right? Thermodynamics is described as the study of energy transformations, right? So in our last example, converting kinetic energy to potential, potential to kinetic. Now, when you're studying thermodynamics, you're usually going to be studying these energy transformations within a certain system. It could be a living system, like looking at a cell or a multicellular organism, or maybe even an ecosystem. If you're looking at something abiotic, you might want to study energy transformations in a power plant, for example. There are different kinds of systems in which you can study thermodynamics. Two examples are shown here on this slide. So first of all, you can have an isolated system. An isolated system is one that cannot exchange neither energy nor matter with its surroundings. So think of like a double insulated Yeti travel cup, right? When it's sealed, you can tip that thing over, nothing's going to come spilling out. Right? So it's perfectly sealed, no matter exchange between it and its surroundings. And it can maintain the temperature of your beverage, hot or cold, for a ridiculously long period of time, right? Remember that temperature is an average measure of the kinetic energy of the molecules inside of that body of matter. And so if your drink stays hot or if your drink stays cold, that means that that energy has no place to escape, right? So an isolated system is one that does not exchange energy or matter with its surroundings. The opposite of that would be an open system. So an open system is one in which you can exchange both energy and matter. Living systems are by default defined as open systems, right? So you can't survive without taking energy in, right? You've got to eat. And then as your body uses those nutrients, those molecules as a source of fuel, you go about your day, go through all this cellular and physical work, right? You give off heat, a form of energy that dissipates from your body and goes off into the surrounding environment. So you have the ability to exchange both energy and matter with your environment. So by definition, all organisms are considered to be open systems. Otherwise, we wouldn't be able to sustain a living state. One more kind of system that's not in here would be a closed system. So in a closed system, you can't exchange any matter, but you can exchange energy. We'll take a look at that a little bit later in these slides. All right, so when we're studying thermodynamics, there are certain laws that apply to the transfer of energy or the transformation of energy. So let's go through the two laws of thermodynamics. The first one's pretty easy. The second one is a little bit more difficult. So the first law of thermodynamics states that the energy of the universe is constant. So this means that you can transfer energy from one body of matter to another body of matter. You can also transform energy from one form to another form, but you cannot create energy. You cannot destroy energy. This is the same thing with matter, right? You can't create it, can't destroy it. You can just shuffle it around, right? So energy can't be created, cannot be destroyed, but you can move it around. So we looked at the transfer of energy from a hot mug of tea to your hands, right? You feel that heat, that thermal energy moving from the hot beverage in your ceramic mug to your hands. We also looked at the transformation of energy, kinetic to potential and vice versa with the divers, right, on that diving platform at the lake. All right, the second law of thermodynamics states that every energy transfer or transformation increases the entropy of the universe. So first of all, you can think of entropy as a disorder of the universe. So this means that every time we move energy around, we're making the universe more and more disorganized. Maybe something to keep in mind is that this disorganization or disorder isn't local, but it's looking overall on a global scale, on a universal scale, right? Every time we move energy around, something becomes more disorganized as a result of it. So I've got an AKA here on this slide, maybe a better way of understanding this particular law. It says that during every energy transformation, some energy is unusable and is often lost as heat, right? So living organisms, we are really good at showing this. Second law of thermodynamics, right? We take really organized forms of energy like glucose molecules and we degrade them, right? We break them apart, we release energy, we use that energy in our bodies to drive cellular work, but a lot of that energy actually leaves our bodies as heat. First of all, it helps to maintain our normal body temperature as part of homeostasis, but it leaves through the surface of our skin, right? And when it leaves into the atmosphere, and then it goes off into the great beyond, into the universe, to increase entropy. All right, so as we are studying now various chemical reactions within living organisms, and we're looking how energy is transferred between organisms or within an organism, we have to understand, okay, which chemical reactions require the use of energy, which chemical reactions consume energy, and then which are the chemical reactions that actually release energy. So we're going to start a discussion of some of these categories of reactions and whether they're going to consume or whether they're going to release energy. The first thing we're going to talk about here is a spontaneous reaction or a spontaneous process. A spontaneous process is one which occurs without any energy input. In fact, it's going to do the opposite and it's going to release energy. So for a process to occur without any energy input, it has to increase the entropy of the universe. So it has to release some of that extra energy, probably in the form of heat, to increase the disorder in our universe. Now, oftentimes we may think of the term spontaneous as meaning quick. In this case, that is not the case. So spontaneous here instead means energetically favorable. It can kind of happen on its own, but spontaneous processes can be quick or they can also take a really long time to happen. Let me give you an example. This is not a living example. So when you're driving down 121, right, trying to get to a store or to campus perhaps, there's a lot of construction going on, and you bought a new car and you love your new car, but driving down 121, a lot of trucks kick up rocks, right? And the rocks that get kicked up, they hit the hood of your car and they start to chip off the paint. And when the paint chips, that exposes the metal that the hood is made out of to Texas elements. And when you mix metal that has iron in it with the elements, particularly water, you have chemical reactions, oxidation reactions that start to happen, and it causes the metal to rust on your car. You didn't have to do anything on your part to get that rust to be there, right? You actually don't want it to be there in the first place, right? This is a spontaneous reaction, spontaneous chemical reaction that happens completely on its own, but it probably takes a while for that rust to start to accumulate until you can actually see it with your eyes. So it's a long process. It happens very slowly, but it's spontaneous, meaning that there didn't need to be any energy input to get that oxidation reaction to happen on the hood of your car. All right, so steering away from the non-living towards the living now, biologists oftentimes want to know in an organism which are the reactions that happen spontaneously, meaning that they're going to happen without the cell having to use its own energy to drive those chemical reactions. In order to determine which chemical reactions are spontaneous, scientists will need to look at the energy changes that occur during a chemical reaction. So that means, what is the amount of energy that you start with at the beginning of the chemical reaction? And then what is the amount of energy that you're left with at the end of the chemical reaction? And so when we're studying these energy changes, really what we're studying is a system's free energy. So let's talk about, well, what is free energy and how do we study this change in free energy when we're looking at whether a chemical reaction is spontaneous or not. So free energy is defined as the energy that can do work when temperature and pressure are uniform. Now, temperature and pressure are pretty much always going to be uniform within a living cell. So you can kind of ignore that part. So just focus on free energy is the energy that's available to do work. And so when we're looking at these free energy changes, right, how much energy do we start with? How much energy do we end up with? At the end of a chemical reaction, what we're looking at is this change in free energy, or abbreviated using the symbol delta G. So if you're unfamiliar, delta in any capacity means change in, and it means the change in whatever comes after it. So we use the capital letter G to symbolize free energy. It can also be called Gibbs free energy, hence why we use the letter G for Gibbs. So delta G indicates change in free energy. Only processes that have a negative delta G are going to be spontaneous. This point probably makes zero sense right now, but hold on to this thought. We're going to come back to it, okay? So only processes that have a negative delta G are spontaneous. Okay. Now, as we look at change in free energy, the change in free energy, or maybe let's say total free energy of a system, is also a measure of the system's instability and its tendency to want to change to a more stable state. So here's where maybe one more time we can bring out our teeter-totter, right? We brought out the teeter-totter when we were talking about pH, right? So you can think of teeter-totter, right? Here's my little teeter-totter. And on one side, we're going to have stability. On the other side, we're going to have free energy. Okay, so you'll notice that when free energy, the amount of free energy of a system is low, the stability is going to be really high, right? Think of a toddler, right? When they have exhausted all of their energy, they've got no more energy left, they're pretty stable, right? You can get them to sit on the couch for a couple of minutes. On the other hand, if you were to flip this teeter-totter around now, anytime free energy increases, that means that your stability is going to decrease. So any system that has a lot of this free energy is going to be highly unstable. And very much like everything in this world, including yourself, right? If you are not stable, you want to get to that maximum state of stability, right? If you don't know where your money is going to come from to get food, if you don't know where you're going to be spending the night, right? These are all things that make you feel very unstable. And you're going to want to do everything in your power to reach a state where you feel stable, you feel comfortable, right? Figure out where your food is coming from, where your money is coming from, where your shelter is coming from. And so this sort of idea belongs not just to you, but in every system. In the surrounding environments, within your body, doesn't matter, anywhere, any system is going to want to reach a maximum state of stability. And a maximum state of stability means lowest energy. So a system that has a lot of energy, right? So a lot of energy, but low stability, is going to want to change so that it reaches a state of low energy, but maximum stability. During this spontaneous change, free energy is going to decrease and the stability of the system increases until that system reaches that maximum state of stability, which we call equilibrium. All right? Now, as a system is going towards equilibrium, right, to reach that maximum state of stability, but lowest energy state, it has to give up all of its energy. Right? So as it's giving all this energy up, that energy can actually be used to perform work for that system, which is great, until the system reaches equilibrium. Once it gets to that equilibrium, that's it, right? No more work can be done because you don't have any more energy to release to pay for that work.